continuing on going over the practice exam. Number 10, what is the wavelength of the line in the emission spectrum of helium ion with a plus, so it's lost an electron, produced by an electronic transition from the 5th to the 2nd energy level? Alrighty, so I want a transition, so I know I can use energy is equal to negative 2.18 times 10 to the negative 18 joules. Since I don't have hydrogen, I know I have to use my atomic number squared times 1 over n final minus 1 over n initial. Alrighty, so I just plug my numbers in. What do I use for Z? Z is my atomic number. What is my atomic number of helium? 2. So then 2 squared. What is my final energy state? The transition from 5 to 2. So my final is 2 and my initial is 5. Great, you have everything set up so you can solve for your energy. You would plug your numbers into your calculator, making sure you're squaring the correct numbers. And that comes out to be negative 1.83 times 10 to the negative 18 joules. I know that this is the energy of my electron. Well, if I wanted just the energy, I'd be finished, but we have to go look back at the question. I want the wavelength. I know that the energy of my photon that's absorbed is equal to the energy of my electron that's emitted. So my energy of my photon is equal to positive 1.83 times 10 to the negative 18 joules over photons. I also know that energy is equal to high C over wavelength. And I can rearrange to get my wavelength. Now there's a Rydberg equation that's 1 over wavelength with a different constant that you can also totally use for this question. I just feel more comfortable with the energy just because it clicks in my head more and I've memorized it. There's no right or wrong way to do it. So then I just plug all my numbers in. Do I have to change anything to the energy? Nope. And I get 1.086 times 10 to the negative 7 meters and convert that to nanometers, which is 109 nanometers. Next question. Experimentally, the electron affinity of an element can be determined by using a laser light to ionize the anion of the element in the gas phase. Given that chlorine's electron affinity is negative 348.7 kilojoules per mole, calculate the photon wavelength corresponding to this electron affinity. What type of electromagnetic radiation is this? Okay, so I have my electron affinity for chlorine, which is negative 348.7 kilojoules per mole. I know that that's represented by this. Chlorine gas, because it has to be in gas phase, gained an electron to become chlorine ion in the gas phase, and it released this much energy. Well, since I want wavelength, I know that I can get that from my equation of relating the energy and wavelength. Now you'd say, well, why do I know I need to use this equation? Because there's other wavelength equations as well. Well, I'm given an energy, and the way that I can relate energy and wavelength is through this equation because I can rearrange it to solve for the wavelength. Well, to do that, I have to make sure I have my energy of my photon. I'm given the energy of the electron, right? So it's working a little bit more backwards than what we were doing up here. The energy of the photon is equal to the energy emitted by the electron. So this negative 348.7 kilojoules per mole for my electron is equal to the energy of the photon, but positive. Awesome. Well, how can I relate that here? What do I need to do? Well, I want joules per photons. Now I have kilojoules per mole. So I have to convert 348.7 kilojoules per mole times 1,000 joules over 1 kilojoule times I want my photons, so I inverse my Avogadro's number. To then get rid of my kilojoules, my moles, and I'm left with 5.80 times 10 to the negative 19 joules over photons. Now that I have that, I can plug it in and solve for my wavelength. The wavelength will equal 349 times 10 to the negative 9, which you can then convert to nanometers. So again, taking it a little step back. You ionized chlorine in the gas phase and it took negative 348.7 kilojoules per mole. Because that's the amount of energy to give chlorine gas an electron, that's the electron energy. What you want is the wavelength that corresponds to this of the photon. Well, we know that the energy of the photon and the electron always relate because the energy is transferred, never created nor destroyed. So therefore, the energy that I'm given of my electron is the same energy of my photon that was absorbed. Since we want the wavelength of the photon, I can always relate back to this equation. But I know that I can't be in kilojoules per mole because my Planck's constant is joules. So therefore, I had to convert back to joules per photons and plug everything into my equation to then get my wavelength. What light does this, or electromagnetic radiation, does this wavelength correspond to? That would be ultraviolet. Awesome. Let's flip the page. So again, because I made the font bigger for video purposes, number 12 is at the bottom of this page for you most likely, but I'm going to flip my page. Number 12. So, the reaction of iron 3 oxide with aluminum to form aluminum oxide and iron is called a thermite reaction, and it's highly exothermic. What does exothermic mean? Loses a lot of energy, so very negative, right? What role does lattice energy play in the exothermicity of the reaction? Well, before we delve too much into this question, what is lattice energy? Lattice energy is the amount of energy that is released when the cation and the anions come together to form your crystal solid. Or it is the amount of energy that the crystal solid needs to absorb to break up into its ions. So since it's really exothermic, we're looking at it as the ions coming together to make the solid. So let's write this reaction to start. Is this a single replacement reaction or a double displacement reaction? Single replacement, because you have an ionic compound in a metal. And this was way more reactive than the iron. It kicked off the iron and formed aluminum oxide and iron by itself. Make sure we balance. Boom. So the energy associated with forming a crystalline lattice from gaseous ion is the lattice energy. I'm going to take that and write that down in my own words because I need to explain what role lattice energy plays, and that would be one reason. Since aluminum ions are positive, right, and oxide ions are negative, this is a -2 and this is a +3, what happens in the reaction is Fe breaks up from the oxygen, and the aluminum ionizes, and these two come together to form your crystal. So since aluminum ions are positive and oxide ions are negative, When these two ions come together, to form their crystal lattice, they lower their potential energy according to Coulomb's law because the opposite charges are coming together, so the potential energy is lowering. When they separate, because of like charges, the potential energy increases. When the lattice forms, the energy released in the form of heat is highly, therefore, exothermic. Because the potential energy comes down, it needs to release all that excess energy, which is therefore the reason that it's so exothermic. According to molecular orbital theory, which molecular ion has the highest bond order, highest bond energy, and shortest bond length? Explain. O2, O2 minus, or O2, 2 minus. So the best way to visualize this is to make a molecular orbital diagram. Now you actually don't have to do it for all of these, but I would do it for the neutral. The neutral is oxygen, and then you can look at, based off of the molecular orbital diagram for oxygen, what would happen if you gain 1 electron or 2. So O2, 1 oxygen here, 1 oxygen here, my 2s and 2p. Alrighty, so what do I form for my molecular orbitals? My 2s and 2s combine to form a sigma 2s bonding orbital and a sigma 2s anti-bonding orbital. I would fill my electrons in one at a time, and I'm done with the s. Now, my p's overlap and combine to make 3 molecular orbitals. They combine to make a sigma and 2 pi's. The sigma, because this is negligible in sp orbital mixing, is much more stable and lower in energy. So sigma 2p first, then pi 2p. This should be lower in energy than your atomic. Then you have pi 2p antibonding and sigma 2p antibonding. And you fill your electrons in one at a time. One from here, one from here, one from here, one from here. Boom, 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 boom. Alrighty, so you have all of these electrons and 2 unpaired in the pi 2p. So let's calculate the bond order, since we're asking for who has the highest bond order. 1/2 times the number of non-bonding electrons to the number of bonding electrons, 2, 4, 6, 8, minus number of antibonding, 2, 3, 4. That's 8 minus 4 is 4 divided by 2 is 2. Okay. Now, I can't really answer this question yet because I need to compare my other two. So this has a minus. So it means it gained an electron. So if it gains an electron, that would be here, right? And that would give me 1 more electron in my antibonding. What would the bond order look then? Bond order is equal to 1/2 times number of bonding electrons didn't change, 8, minus number of antibonding. I gained 1 antibonding electron, so 8 minus 5. That is equal to, 8 minus 5 is 3, divided by 2 is 1.5. What about the last one, 2 minus? So I gained 2 electrons. So I would have one here and then another one here. So then my bond order would be 1/2. My bonding didn't change, but I gained 2 antibonding, so minus 6. 2 over 2 is therefore equal to 1. So now you can answer this question. Which molecular ion has the highest bond order? O2 has the highest bond order and bond energy. Which one has the shortest bond length? Well, when you have the highest bond order, it also has the shortest bond length. Now, it's not in this question, but I'm going to ask you this. Which one is the most stable? Oxygen. Oxygen is the most stable because it has the shortest bond length due to its highest bond order. Remember, the longer the bond is, the easier it is to break, the less stable it is. And that's it for this page.